So anyways, welcome to Canvas for August 24th, 2020. Today's speaker is Niyash Afshordi from Waterloo Perimeter Institute. Niyash got his PhD in 2004 from Princeton and is now on the faculty of Waterloo and part of the Perimeter Institute. So today he's going to talk us about a new way to measure mass. So take it away, Niyash.
Thank you very much, Dennis, for this great introduction. And thank you guys for joining us during this beautiful, beautiful day in August. At least when I'm looking out of my window, it's very pretty here. I'm not sure elsewhere where you're watching this. But the fact that you are here means that you're sacrificing your great day outside. So I really appreciate that. So today, I want to use this wonderful opportunity to reach across, I guess, the continents and tell you about a new way to measure mass. Of course, introduce myself and tell you about the kind of science and astronomy that we do in Waterloo, as this wonderful series has been introducing us to all different kinds of astronomy that's been being done across Canada. So. Unfortunately, as some of you have learned, that my pointer cannot be seen. So I'm going to try to use my words to point you in the direction in which you should focus your attention to, but hopefully that shouldn't be too much of a problem. So let's get started. So first of all, this is in collaboration with two wonderful students, graduate students at University of Waterloo. I should say former graduate students at University of Waterloo. The work was led by Tianyi Yang, who was a master's student with me and Mike Hudson at U Waterloo, who is now starting a PhD program at the University of Edinburgh. And with Supranta Bora, who was also was a PhD student at University of Waterloo, graduate, but a PhD student at University of Waterloo. And he worked with Mike Hudson and Azal Gishnizjani. But he's starting a postdoc at University of Arizona, basically around now. So they both have left Waterloo, unfortunately, but they have spearheaded this great work, which was part of their theses. And I'm not sure if Tianyi is here, but he was supposed to join us if he's, and so if there are questions that I cannot answer, if he manages to join. Tianyi, are you there? Okay, I don't know if he hasn't made it. I guess it's now past midnight in China, so that's where he's visiting right now. But if he does show up, I can point questions towards him. Questions I cannot answer. Okay, so let's get started. So this is a work. It was I guess submitted to arXiv almost about a year ago. In fact, yeah, so the original form is August 7th. And was published sometime early this year, just before the pandemic hit. So you can find it on monthly notices and also on arXiv, which has the updated version. So let's get started. Of course, you're all astronomers or astronomy enthusiasts here, so you all know about the Milky Way, the band that you see across the sky. If you go out into the wilderness, away from the city lights or in the backcountry, so this is what you see from the stars as we sit in the middle of the disk of Milky Way. And the picture we have, which we cannot directly see, but we can construct from observations from the Milky Way from the top, is what you see on the bottom right. So we live in a spiral galaxy with a bar in the middle, which you cannot directly see, but we can infer based on the stellar motions. On the bottom left, you see a cartoon of the structure of the Milky Way, which is the famous disk. In the inner kiloparsec, you see the central bulge. And of course, the galactic center, there is a black hole sitting at the very center. And then surrounding all of this is the halo of the Milky Way, where you have global clusters and then you have the halo stars. The sun, of course, sits within the galactic disk, about 8 kiloparsec away from the center. Now, the great revolution in galactic astronomy, which I'm sure you have heard about, has been the launch of Gaia. which has been mapping or advancing the map making of the Milky Way by many orders of magnitude. So now we have 3D positions and velocities for almost 1 billion stars. Something that was not possible. I mean, the last version of Gaia was Hipparchus, which only did it for a few thousand stars. So we had basically improvement by almost 6 orders of magnitude, 5 or 6 orders of magnitude on top of Hipparchus. So Gaia has really revolutionized galactic astronomy and has increased precision on many of our statements about galaxy by many orders of magnitude. So we have 1.7 billion stars in this map. So this every point is a star in this map. And of course, you do see galactic dust where which extincts the stars. But nevertheless, we can see many stars using Gaia. And this is a movie that shows the measurement of parallaxes and proper motions, but with some exaggeration in Gaia catalog. So here I'm just going to try to run it. So this is a movie that's being run from the Gaia collaboration. So this is like a still image at first, but then you see the parallax motions. Of course, this is much, much bigger than what you actually see in the sky by 5 orders of magnitude. And if you keep watching, you see these parallaxes are there for a while. So just because Earth goes around the sun, the stars move around. The ones that are closer to us move around more. But of course, there is some projection effects as well. And you see the constellations that are kind of wandering around. But now the movie changes pace. And now it actually increases the speed by 12 orders of magnitude, showing proper motions of the stars. But the stars are moving at 12 orders of magnitude faster than they are actually moving in the sky. And you see that basically when that happens, all the constellations disappear very quickly because the stars move around. And then you see even the more distant stars are starting to move around. Of course, the more distance they are, their motion is less noticeable, but you see that the structures, even the disk of the galaxy, it becomes more and more blurry, simply because here you're assuming that there's a constant proper motion that doesn't change with time, so everything just moves around quite a bit. So this is a kind of measurement, or it is a visualization of the kind of measurement that's been done by Gaia. So for both parallaxes, of course, as you know, parallaxes tell us the distance to the star. But the proper motion, as well as the redshift that you could measure, gives you from the spectra, gives you the 6-dimensional phase space information for all basically hundreds of millions of stars. So what do we do with all this information? Possibly the oldest equation that has been used in physical astronomy, or in astrophysics, I should say, is the formula for Newtonian gravity, or in particular, the relationship that relates the velocity of circular orbits to the mass and distance, or I guess another way of writing Kepler's third law. And what's special about it is that if when you measure velocities, and if you have a measure of the size, which is r here, then you can get mass. And to a good approximation, this is how we've been estimating masses in astronomy for the past 4 centuries, basically. So the velocity is something you can measure for stars in general, or you could, of course, use gas as well. So the mass could be dark matter and other components, but we know within the galaxy, at least on larger scales, it's dominated by dark matter. And this is basically what you do. If you have a measure of the size, say from distance ladders or from standard candles, or other methods, from parallax, for example, and if you have a measure of velocity, you can get mass. However, there's a caveat in using this equation, which is the fact that mass distribution is not as spherically symmetric. So this equation needs to be corrected to account for the fact that deviation from a spherical symmetry, but also orbits are not circular, and that's something else that needs to be accounted for. Now, one of the one of the ways that we get around this problem that they can, so let me just, so basically there are two caveats here. The mass distribution is not spherical symmetric and orbits are not circular. So at least the second caveat, and to some extent the first caveat, the way we can get around them is by using an average version of this, which is called virial equilibrium or Jeans equation. I can see there is is there a comment for me or a question? I think okay, thank you. I just saw a very cool movie, thanks a lot, okay. Of course, I don't get any credit for that. So we can use virial equilibrium or Jeans equation to get to do this if we don't know the orbits exactly or if they're not exactly circular. But then to do this more properly, we had to make assumptions because the velocity wasn't directly observable. And the other question is that, is there really equilibrium? And equilibrium is an assumption which makes things simple, but in reality, that's still an assumption that needs to be justified. So basically the short story is that measurements of mass, while we've been doing that for the past 4 centuries or even more, always has caveats and systematic errors, which basically come from these unjustified or sometimes unjustifiable assumptions. And we'd like to be able to make progress. So not assume circular orbits and not assume virial equilibrium, and nevertheless be able to estimate the mass. So how can we do this? So to do this, I want to introduce some terminology, which is something probably you've already learned at some point in graduate school or even undergraduate and forgotten about it, but some of you might still remember. These are known as action variables. That's a really cool name for something that's used so rarely. So these are these integrals of motion, things that stay constant along the orbits of particles that move in constant potentials, or even a slowly varying potentials. So technically they are an integral or the area of the phase space for different projections of the orbits in different directions in the phase space. So in 3 dimensions, you would have 3 position variables, 3 q's, and then 3 momentum variables, 3 p's. And then if you have an integrable potential, then in general, you have 3 integrals of motion. And in particular, you will have 3 action variables, which are defined as basically area of the phase space orbits in all the 3 coordinates. So these are constants of motion as long as the potential changes slowly. And usually it's hard to get these. So actually, let me show you in the figure you see on the right. So these orbits, basically the radius or the area of the orbits is like J. And then the angle is what's perpendicular to it. So orbits would usually be moving on toruses. An area of the torus in various directions would be different angle, different action variables, which are constant. So in practice, estimating these action variables is not easy. So that's what we do then is to use approximations. In particular, there's a so-called Stackle approximation, which was introduced by Binney in 2010. So James Binney suggested that you could approximate any potential, at least locally, as a Stackle potential. And a Stackle potential is nice because it's an integrable potential. So you could, using the phase space coordinates, estimate the, basically using the phase space coordinate and using the potential, at least the local derivatives of the potential, you could get the action variables. Now, these are not the exact action variables because the real potential may not be integrable or may not be close to Stackle, but they approximate the true action variables if they exist. And in particular, this was implemented by Joe Bovey in the GalPy package. So Joe Bovey is at University of Toronto, who made this publicly available package in Python. It's very useful. We heavily made use of this GalPy package for our analysis. So now the nice thing about actions is that you could actions can be united. So you don't have just one star that has a constant action variable. You could have a cluster of stars. Now what happens about what happens to a cluster of stars, let's say dwarf galaxy or a global cluster, that falls into the gravity of some large object, is that they could be, and in general, they will be stripped by tidal forces. But nevertheless, since action variables are constants of motion, they remain clustered in the action space. So even though you might have an object that's been completely tidally stripped, so there's no gravitational binding of its members anymore, it is still clustered in the space of integrals of motion, and in particular in the space of actions. And this, you can actually see this visually in these shell galaxies. This, you see the picture of it here, where you see these shells that we believe they are remnants of a galaxy that's been tidally stripped by the gravity of the central parent galaxy. But nevertheless, some structure remains, and this is a structure that's not tidally bound, but something that's noticeable because all of these stars share the same initial conditions, and so basically very similar action variables. So the main idea behind our approach then is that these action variables should be constant and should be clustered for these kind of structures. But if you use the wrong potential, then you get the wrong action variables that would not be constant, and you would get a weaker clustering or weaker structures in the action space. So the central idea then is that you want to find the potential that that maximizes the clustering in the space of integrals of motion or in the space of action variables. And this is an idea that was first suggested by Sanderson and company. In fact, Sanderson, David Hogg, and Joe Bobby, I believe, in 2015, although they didn't actually use it on real data because Gaia data didn't exist at the time, and you need all the 6 phase space coordinates to be able to do this in a useful way. So when Gaia came out, then we got started. And again, another demonstration of this is that the action space is very clumpy because initial conditions is hierarchical and clumpy. So here are just kind of 2 cartoons of this when we did this, I guess, more than 10 years ago. If you look at the top left, we kind of have a cartoon of tidal disruption of a one-dimensional object, which kind of wraps around phase space. And what you see is that if you look at the space of action and angle, the action looks very clumpy, just because it doesn't change with time, even though the angle is completely phase mixed. So the angle over time, things are phase mixed in the angle direction, but in the action, they remain clumpy. And the interesting thing about the action space is that you don't need to look at the entire sample of your stream, your initial condition. If you look at the subset, you still see this clumpiness. And that's what you see on the right-hand side. That, of course, the actions are unchanged, but if you look at the subset of your observable region, of course, you can never see everything, right? Some may go behind the galaxy, so we've been missing part of the initial stars that were part of your galaxy or global cluster. But nevertheless, the distribution in action space is clumpy. It's even clumpier than it would be if you saw everything. And this is one of the interesting features, this kind of lattice structure, as one of the interesting features of looking at the action space, and in particular clustering in the action space. So that's basically what we are going to exploit for our study. We look at the correlation. Of course, I do come from a cosmology background, and cosmologists love to look at correlation functions. Galactic astronomers don't usually do correlation functions, but cosmologists do that all the time. And our idea, in fact, Ed Bertschinger and Roya Mahayai back in 2009 was to look at the correlation in the action space. So correlation function in action space is basically you look at the pairs, or in general, correlation function, this is how they look. You look at the number of pairs that you see as a function of distance of the pairs. So this is this P log D. Log of D would be the log of the distance. And the distance in action space, we define it, you have to kind of define a metric. So here we define it by normalizing to the variance of the difference. So if you see a pair of stars in the action space, so these are 3 action variables, you look at the difference of the actions, and then you divide it by the variance, square it, and then divide it by the variance of action variable in that direction. And then when you take the square root, then that would be the distance. Like this is just like Cartesian distance, which is the simplest thing you can think of. but we have to normalize it somehow. So we divide it by the variance. So you could look at the probability distribution of log of this d, and that's just like a histogram. But what we want to do is we want to compare it to what you should get if you just had uncorrelated distribution of stars. And there is a little bit of art in doing that, because we don't really know on larger scales how this d should look like, this distribution of d. We know on a small scales, it should be just basically go as d cubed, because if you just have random distributions in 3 dimensions, the probability of finding things at some distance would go as distance cubed. But then on large distances, then it really depends on the global structure of the galaxy. And then we have to kind of normalize this somehow. I'm going to get back to this. So there is basically an assumption about what this P uniform should be. And if you divide this probability, the observed probability of the distances divided by the uniform probability, then you get the correlation function, or in particular, 1 plus the correlation function. So this means that for a uniform distribution, if you just had random sprinkling of stars in action space, then psi would be 0. But if the stars are more clustered in action space, if you have a hierarchy there, then psi would be positive. If they are anti-clustered, they kind of try to avoid each other, then in the small, at least at a small distances, you're going to get negative psi. So this is kind of our measure of correlation, which is essentially the same correlation function, or exactly the same correlation function that cosmologists use, say, for galaxies. So Jim Peebles, who won the Nobel Prize in physics last year, one of his big contributions was actually measuring this correlation function back in the 80s for galaxies, and finding out that it was a power law. Now, of course, there was the real space, not the phase space or not the action space. Here, we're looking within a galaxy, in particular Milky Way, and we're looking at the distance in action space. On the right, you actually see the measurement of this quantity, or in particular, 1 plus psi, as a function of, well, actually here we don't normalize it necessarily properly, because we don't know exactly what the right normalization. So we just divide P log D by D cubed, which is probably the right scaling on a small scales. And you see that it approximately becomes flat. That would be basically psi becoming 0, but with the normalization a bit off. So if it was properly normalized, it would just go to 0, because log of 1 is 0. So here it goes to 5, just because we don't know how to normalize. And large Ds, at large distances, you see that this is falling off, simply because on larger scales, you don't have uniform distribution. You just run out of pairs at very large separations. And basically, where we want to look at is log Ds, which is less than -1, as we're going to discuss why. But that's where basically you're going to have a small scale clustering. And for comparison, the biggest structure that people have discovered in Gaia in the phase space is this so-called Gaia Enceladus sausage, or a stream. I forgot actually the term that people use for it. Gaia Enceladus structure in the phase space. I guess they call it Gaia sausage, and maybe there's another name for it, which I forgot. And they seem to be actually at larger separations than the structures that we're looking at. So we're looking at things that are very, very clustered in a spatial initial condition. So anything to the left of the dashed curve. And the Gaia Enceladus is this orange structure to the right of it. And then we have actually a detailed derivation of what we think is the likelihood. I'm not going to walk you through the derivation, but basically what we should be doing is doing an integral over this P log D it's something like an entropy, but with a minus sign, it turns out. And in fact, it's called KL entropy. So there's, what it does is that basically we're trying to maximize the clustering that you see in this structure, which is kind of opposite of maximizing the entropy. So when you maximize the entropy, you get the most uniform distribution. Here we want to do the opposite of that, which is kind of integral of P log D log of P log D. So we're going to get the kind of the clumpiest or the bumpiest distribution you can get. And the way we do it is that we take the dark matter potential and we keep changing it. We change the power, assume it's a power law. We change the power and the normalization until we get a maximum clustering in this action space.
Yes, we have a question for you.
Go ahead.
Can't you use that extrapolation to small d to give you the normalization you need?
We can, but the problem is that that's also kind of the data we need, because so we want to maximize the clustering. So if I just set that to 0 at the small d, then I kind of lose all my information. So the information is really kind of the bumpier you get, or the more structure you get at the small d's, the better it is. And I can, but that's not actually my focus. So in a sense, in terms of log likelihood, that just changes log likelihood by a constant. And indeed, I think the answer is yes, but that's not really the focus of my exercise. But that's a very good question. I'm going to show you, in fact, how much things are going to change. So things look kind of innocuous at the small log d's, but in fact, all the interesting action is happening there. So we don't want to kind of lose any information there. That's why we didn't really add any initial normalization. So we're going to come back to that, but it is a little bit of a technical point. But thanks for the question. Other questions? Okay, so if not, was there more? Okay, so I cannot hear anymore. So another point is you have to decide this integral, basically how far you want to go. And there is this kind of arbitrary choice. What is your max d max? How big, how separated your pairs can be. And the problem is that if you go to very large separations, then you're going to mix kind of the general structure of the galaxy with the distribution of pairs. So you need a cutoff. And we have to make sure that basically if this cutoff is very low, very small, then you're going to get large errors because you have very few pairs. And if it's very big, you're going to get systematic errors because you're mixing the structure of the galaxy with the structure of the pairs within the galaxy. So, so we're going to talk about the dependence on Dmax, which is kind of our biggest systematic control and systematics. So that's basically ingredients. This is kind of the most equation heavy slide. So I hope you forgive me for that. But the main idea is that we have a likelihood that maximizes clustering, and we have a dark matter potential we try to fit. So in practice, this is kind of what it means. So here is just some simulations that we've run where you kind of start, you take a potential, you throw a bunch of stars in it that have the same initial conditions or similar initial conditions. So here you have JR and J phi that you're showing here, 2 of the action variables, 2 out of 3. So here only I show JR and J phi. I'm not showing JZ here, but that's another variable that we could plot. So there's really a 3-dimensional distribution. And you could let it run basically using just solving Newton's equation in the potential that you assume. And here we assume some power law potential for dark matter, and we have some potential for the bulge and some potential for the disk that we're not varying. We're just interested in the dark matter potential here. And then what we do is that we try to, we kind of, even though we run the simulation with one potential, we get the action variables using a different potential. And of course, since as I was saying, if you use the wrong potential, your actions are not going to be constant, then you're not going to get a cluster distribution anymore. So in all of these panels, the middle one is basically I run the thing with one potential, or I should say T&D runs this with one potential, and then we infer the actions with the same potential, and you see that they look kind of tight. They're very clustered. And here there's just a single stream or a single kind of cluster, or initial cluster, if you want, that's being tidally stripped. But then on the left, you see the wrong, left and right are you changing the parameters of the potential when you infer the action variables. And since you're getting the wrong action variables, then you see that the structure is much more sparse, or much less compact. And that's because basically these action variables that you're inferring using the wrong potential are the wrong action variables. So they're not constants of motion anymore. So you're starting basically to spread over time, and that's why you get this more spread structure. So the name of the game is that just you keep varying potential and see when you're going to get the most compact structures in this space of actions. Now here we have only one cluster, so it's very easy to see it visually, but of course, if you have lots of these initial clusters, because the structures, I mean, galaxy forms hierarchically from many of these, then it's going to be harder to see it by eye, but you could still measure it statistically, and that's what we try to do. So this is kind of the statistical measure of how this works, and this is a simulation again. So again, the same simulation that I'm showing you, just a single stream. So on the left, you see basically the likelihood surface. The plus is the correct variables for the index and the normalization of the dark matter density profile. And the likelihood values that we see are what you see in red, or I guess in colors. So you see that you're close to the correct value, but you're a little bit off. And it turns out that, I mean, there is a systematic error. So in fact, the amount by which you are off doesn't overlap. At least for the normalization or for mass fraction, it seems that it's close for these two simulations. But for the index, which is the power, you're off. Not by much. It's about like 4% that you're off in the power law index, but it still is bigger than the systematic errors. And here you just have a single stream that we're simulating here. So this suggests that at least with this, in this particular simulation, the systematic error is bigger than the statistical error. So it's around, but they are tiny errors compared to kind of errors that we're talking about these days. So around 1% error in normalization and 4% in the power law index. And the reason we think we have this problem basically with the simulations is that basically this statistical approximation is not perfect. So you're not going to get exactly the right potential because you don't exactly have the right action variables. A statistical approximation approximates this power law potential plus disk plus bulge as a statistical, which is not really correct. And this is the level of uncertainty we're going to introduce by a statistical approximation, of order of a few percent. I should say that, I mean, in principle, that can be avoided, but it's going to be much more time consuming. You can calculate the actions exactly, but it's going to take much more time. So interestingly, when you add the background of the stars, not just the streams, but the background of the stars, then things actually get better, which is a bit surprising. But if somebody is interested, I can tell you a bit more why we think it actually gets better. So what you see on the left here is actually, as you're changing the potential and looking at this correlation function, you see that, I mean, as you keep changing the potential, the correlation function gets a larger peak at a small d. And this is exactly what we're looking for. Basically, our likelihood, which has some formal definition, all it wants to do is to maximize this bump at a small d. So even though, I mean, the bump is small, still the idea is that you could infer which potential gets you a bigger bump, and that's going to be the correct potential. And if we use this, so the left, you see these simulations that we've done, and in fact, the correct potential is what to say is FH, and so basically the dark matter fraction in the potential is within the solar radius is 35%, and the slope is 1.7. And it's a bit hard to see the colors, but the biggest peak that you see there, which is in purple, is in fact the correct potential. All the other ones basically give you a smaller peak, more widely distributed and a smaller peak. And that's basically why they're disfavored. So basically the method is giving the right potential. And on the right, we kind of plotting the mass fraction that you infer compared to the correct one. The correct one is in the dashed horizontal line. And the inferred one in the blue points. You can ignore the black points for now. And you see that they're basically within 1 or 2 sigma, at least for a small d maxes. And basically the idea is that you look at, you kind of keep increasing d max until you see a big jump. And that's very basic, you don't trust it anymore. So that's what we do to pick our d max. Because if you pick a very large d max, you're looking at these very wide pairs that are size of the galaxy. And then we don't trust this analysis anymore because it's not the small scales. And you see that basically you always see this plateau at the small d's that are consistent with the right result within 1 or 2 sigma. But when you see this jump around log d of -2, then that's basically where we stop. And this is based on the simulation. So we take this lesson from simulations and then apply it to real data. Any questions so far before I go and get into the real data?
Yes, we have one question here. So you're using just the solar neighborhood for your analysis, so the potential can be approximated with the power law? Question?
That's a great question. No, we're actually going farther, and we look at different power laws as a function of distance. I'm going to describe it in just a minute. In the simulation, we just have a single power law, but in fact, we look at different distances, and you can get different power laws for different distances, and that would be a great consistency test of whether we can then see whether they're consistent with each other. Thank you. Other questions?
Not at the moment.
Okay, thank you. Okay, so now let's look at the real data. So now if we do this exercise for real data, and I think actually maybe I do have, I don't have, basically we have just two sets of distances. So so we have 9 to 11 kiloparsecs. So we look at all the stars between 9 to 11 kiloparsec from central Milky Way, and then from 11.5 to 15 kiloparsec. So those are the two distances that we look at. So here, this is for 9 to 11 kiloparsec that I'm showing. But I'm going to show you all the results for for the other one as well. So here I'm just showing that what actually happens with real data. So this is the distribution. It's a bit tiny, but this is again similar to what I showed before with JR and J phi. So J phi is the angular momentum that shouldn't change. JR is the radial action variable that does care about the potential. And here again, I'm changing the, these are all different potentials. We keep changing the potential basically. Here in this case, unlike the simulation, we don't really know which is the correct one, right? We can keep changing. So this is a two-dimensional parameter space, right? And we can keep changing this and see which one gives us a tighter distribution. Now, here we don't get just a single cluster because Milky Way is not made out of a single cluster of stars. It's made out of lots of things that have kind of been accreted and then tidally disrupted. So you do get some distributions that look tighter. Basically, JRs have a smaller spread, and some that are wider. And in fact, the interesting thing is that this both gives you a disk of a Milky Way because, of course, disk has zero radial action, but also it can give you a streams. So in a sense, you're kind of combining two measurements together when you minimize the spread. You kind of get the circular velocity, but also you get the thing that gives you the tightest the streams in the action space. So it happens, they both happen simultaneously. And basically, if you do this exercise and use our likelihood, then you're going to get, so this is for real data, again, for the same, for 11 to 15 for 9 to 11 kiloparsec. So if you can keep changing the variables and then look at this correlation function at the small distances, and then you see that some of them give you a small clustering and some of you give you a big clustering, right? So there is one value that maximizes clustering at small distances. And this is, of course, a two-dimensional space. In general, it could be higher dimensional, but we can use MCMC or use other statistical techniques to kind of define averages or means and variances or errors in that space. But the main idea is just maximize this curve. And this is what you get. So this is the posterior distribution you get for mass fraction as a function of Dmax, and then for a spectral index, or I guess a power law index as a function of distance. And I mean, like other real measurements, this can be multi-peaked. In this case, you see for mass fraction, you could have, if you increase the Dmax, especially, you could have multiple peaks. And here you see also what happens, that for a small Dmax towards the left, you have fewer pairs. So it looks more like a Gaussian distribution, but you have larger errors because you look at the small number of pairs. And then you look at the right, you have tiny errors, but you can get multiple peaks because then you have basically a small errors, but your likelihood doesn't necessarily have a single peak. And as I was saying, you could also be you could also have other systematic errors for large Dmaxes. But this is generally the nature of things. That is that there is a sweet spot for Dmax that basically we don't want it to be too small because the errors are going to be huge. You don't want it to be too big because then you're basically going to be inconsistent with the simulations and with the correct results. And here are actually measurements as a function of Emax for the mass fraction. And so I'm showing both 9 to 11 kiloparsec and 11.5 to 15 kiloparsec. So we're assuming parallel in each of these radial regions. And of course, we're going to compare whether they're consistent with each other. This is, of course, an approximation as well. And the other thing I'll show is here, you see red error bars and green error bars. So the red error bars, we are kind of attempting to get only the best stars for our measurements, where the errors are tiny. They are basically, you have less than 20% error bars on everything. And also you put a vertical distance cut. So basically you want to get the halo stars, things that are outside the disk, kiloparsec outside the disk. But then in green, I'm including everything, right? All the stars in Gaia in those distance bins. And of course, what you see is that, of course, if you include all the stars, then you may get a good, much smaller errors, but then they're not necessarily free of systematics. And what may be happening close to the, if you include all the stars, is that you may have to model the disk more properly, or there might be other systematic errors that we don't know about. So at the end of the day, there is a statistical error and there is systematic error. And we kind of consider the difference between green error bars and red error bars as a measure of the kind of systematic errors that this method has, which is, since we are really doing it for the first time, it's really unknown what are the main systematic errors, what are the dominant systematic errors. So we're kind of just guessing here. And it looks like basically they are comparable to each other. For the mass fraction, there doesn't seem to be huge systematic error. But for the power law index, there seems to be a order, let's say around 10% or 5 to 10% systematic error, depending on which subset of stars you look at. And of course, if you look at different subsets and you give different answers, that means that you don't exactly know what is the right answer. So that's a way of quantifying your systematic errors. So this is a comparison of what we find for circular velocity, which is really just what I was showing you is a square root of gm over r for everything in the Milky Way as a function of galactocentric radius. And we actually did the thing on the left and we got those very low numbers, but then David Hawk pointed out to us that the distance and velocity of the Milky Way has been updated in the past kind of 2-3 years due to gravity experiment. That measures the position of basically the Sagittarius star very, very precisely and the velocity very precisely. So if you actually, when you updated that, we actually got the purple region on the right. You see there are 2 different bands for the, sorry, let me just get rid of it. You see these different bands for these different distance ranges, and they are more or less consistent with each other. So the power law approximation wasn't terribly bad, but I mean, there's a little bit of offset. The other thing you notice is that, I mean, of course, other people have measured this as well from the more traditional methods, and then they got inconsistent results. So the most recent one is due to Eilers et al. That use Gaia data as well, but they use Jean's equation and they use red giants in Gaia. And you see that the red curve is consistent with what we got. We are a little bit lower, but within 1 sigma errors. But then other measurements, say from Macmillan that use global clusters, or Vasiliev, actually I'm not sure which, I think Vasiliev uses global clusters, Macmillan, I forgot, maybe uses measures. They are larger, so we get a smaller values than those, but then we get comparable values to Eilers et al. So so the right, and apparently solar coordinates makes a huge difference. So you have to get the right solar coordinates, basically velocity and distance. So that's our result. And it's interesting because this is the first time this method has been used, and it seems to be consistent with traditional methods. So I guess this is reassuring. But I mean, ideally, you want to figure out what are the systematics, and ultimately, you want to use this more forcefully. For example, the green curve that you see here, you see there's this tiny, tiny green bands that kind of go around solid black curves. They are including all the stars and not just the kind of the best stars for our analysis. And you see there's a little bit of offset that I was talking about before. So that's kind of the level of systematic error. So if you're comparing the black solid line with the purple solid line, that's the level of systematic error, because basically if you use all the stars or just the best stars, that's how much shift you get in the results. So has anybody else tried this? I mean, it's been a year since we posted our paper. And in fact, this paper came out last month by Reno et al. Reno et al. In fact, Robin Sanderson is also a co-author who was part of the original team who proposed the method. So here they actually identify specific streams in Gaia and then do this exercise just for those streams. So the pro is that there is no background for this. So you don't have to worry about all the stars that are not part of the streams. The con is that you have much fewer stars and you get much bigger error bars. And here you could see on the right that for different streams, you get these large error bar regions. Some are consistent with Euler's. So these are the points that you see. The same thing that I was talking about came from Giants in Gaia. But some are bigger and again with huge error bars. Basically, I mean, the fact that these seem appear to be inconsistent with each other, maybe at around 2 sigma level, suggests that there are systematics to be understood. So these are kind of two choices you have. You kind of use the best stars for your analysis, but your errors get big, or you could use more stars, and then you have to decide, try to understand your systematic errors. Okay, so good. And then I think one last issue I want to mention is that we could ask whether actions remain constant, and we should look at simulation. This is an example of actions that been looked at in, I think, in fire simulations. And here you see that these are like 3 particles that have the same action at late times, and these are realistic galaxy formation simulations. But then you see that the actions are, I mean, of course, very different at early times, but even after, I mean, the galaxy has merged and realized, the actions could be a little bit different. So that's another issue that needs to be quantified using simulations or maybe other methods. Okay, so let me wrap up. So this is the slice of the action. We introduce a new method to measure mass in astronomy. We don't make any assumption about virial equilibrium or circular motion. We get a smaller mass for the Milky Way, or at least on the small side, compared to other measurements, although it's consistent with the latest Gaia measurements. Future is, of course, bright and exciting. This is the first paper on this. There will be more tests with more simulations. Sorry, to understand various sources of error, like fire simulation that we're working on with, at least we're thinking about working on. And then there could be, of course, more Gaia data that could help. Okay, thank you very much.
Thank you. So if you have questions for DIS, you can either put them in the chat window or raise your hand in the participants list. I will start out. So what difference will the future releases of Gaia data make as they increase the precision of proper motions?
So that, I mean, I think, so there are, I mean, like any data releases. So I mean, we haven't looked very specifically on what difference it might make. But I mean, like any new data releases, we could kind of compare the new data with the old data and see whether they're consistent with each other. And of course, the more stars we have, the more precisely we could measure this to larger distances. So I think there would be an incremental increase. Increase in precision. Whether there could be, I mean, more kind of more revolutionary changes. I mean, if there are systematics that are better understood, that could, of course, make a big difference. I mean, one of the things that we are very sensitive to is that we want to look at pairs, right? So if you have 2 stars that are very close together in the phase space, similar positions and similar velocities. Now, if there are systematic errors that affect how these are measured, or your velocities are systematically off, say for red and blue stars, they could destroy the pairs. And so basically, whatever that destroys the pairs could kind of destroy the sensitivity of this method. And so if something like that happens and we discover that there was a systematic error that was kind of systematically tearing apart pairs in the action space or in the phase space, if that's corrected, that's going to basically make our method much more appropriate or much stronger. The main thing is that we rely on existence of these pairs. If these pairs are not there, then our method doesn't do anything, right? And so the more of these pairs are there, the better it works. And of course, the smaller the errors, the better we can find these pairs.
Thank you. Any other questions? Okay, can you back up to your results slide there?
So I have the real data. I have.
No, go ahead. The one that shows the velocity versus galactocentric distance. Yeah. So there's a discontinuity, right, between the two sets of data you used.
That's right.
So it's interesting. The green line is above on one and below on the other. So I'm just curious as to how you explain that.
Yeah, I mean, of course, I mean, operationally, it's easy to understand what's happened. So we basically divide up the data to two sets, anything between 9 and 11, and everything from 11.5 to 15, or I guess 9 to 11.5 and 11.5 to 15. And when we fit a power law to each of them, and I guess we get different power laws. The fact that for the purple bands, they're consistent within 1 sigma, that means that the power law wasn't crazy, at least for that.
Okay.
For the black one or the green bands, you have tiny errors. And then the fact that there's a discontinuity, it could just be that the power law may not be the right approximation, but the other thing could be that just you have much bigger systematic errors. That needs to be, and this is kind of the point that I was making, that basically the inconsistency between the purple line and the black lines, or the purple band and the green band, that's really the level of systematic errors. So yeah, so that's where discontinuity comes from. And yeah, I mean, I think it gives you a level of inconsistency, well, the level of systematics that you kind of expect, at least if you include all the stars.
Okay, thank you. Is that Julio has a question?
Yes, thanks. Hi, Nash.
Hi, Julia.
My question was, it seems that, you've done quite a bit of work, but the actual application seems a little bit, limited, for all the work you've done. If you all you want to do is estimate the cyclical velocity around the solar neighborhood, that doesn't. So can you extend this method to something like, for example, estimating what is the mass distribution of Milky Way outside the inner regions?
Well,
I guess you're limited by the fact that all these methods rely on orbits. Orbits depend on the gradient potential, not the potential, and therefore you're basically blind to a lot of mass that could be outside, provided it has spherical symmetry. But I was just wondering if you can explore, for example, the high velocity stars, or apply that to that regime and get some idea of what could be, this sort of mass or escape close to the escape velocity, which would probe, the mass of the galaxy well beyond the solar circle.
Thanks, Lee. No, that's an excellent question. I think one of the limitations of this method, if you try to go farther, is basically distance measurements using Gaia. Because we do rely on 6-dimensional phase space information, and then, I mean, if you go farther away, the errors and parallax become big.
You can just use velocities, right? You can just close stars with high velocities rather than far away stars.
Yeah, no, I think this is that's really the direction we should be going. But if you notice, one thing that I didn't talk about a lot was the errors in Gaia measurements. So we were mostly focused on kind of the statistical errors. I mean, the Poisson error in basically how many stars we have at a small separation. But the other error is, of course, I mean, the measurements and errors. The parallaxes and proper motions are not measured very well for distant stars. And I think in principle it can be done, but we have to do basically more statistics. You have to kind of marginalized over all the errors that we get from Gaia, which, I mean, there are a lot of them. So that does takes more computational time, but obviously that is, I agree with you, that's very interesting things are happening, but surprisingly there is enough discrepancy already on these distances, I mean, as you notice by these various measurements. So even though you would think, I mean, more interesting things are far away, it seems that we don't even understand this circular velocity by just difference between these measurements already at, I don't know, 11 and 12 kiloparsec. Yeah, so I think there's something to be learned here, but obviously we want to push it as, I mean, farther, and of course get control over all our errors as well.
Another question, I guess it's in the chat window, so I'll read it out. Thanks for a nice talk. Milky Way potential is not an integrable Stackle type. Will that be a source of irreducible error in your conclusions?
That's another excellent question. Now, of course, there is a mathematical definition of integrability and there is a practical definition. So mathematical definition, of course, you can go and read it in, say, Arnold's textbook, or but whatever your mathematical mechanics you have, which is, I mean, you want to look at the limits of two pairs being very close to each other and see whether they're exponentially, whether you can find, I mean, mathematically 3 integrals of motion, or whether if you cannot, there will be chaos that you could define it mathematically. Now, the practical definition is, of course, I mean, universe doesn't last forever, and these potentials are not static either. So the mathematical definition of integrability is kind of useless at the end of the day. Yeah, I think my son is asking for popsicle now. So that, so my point is that at the end of the day, I don't think we have to be very precise about terminology, because, I mean, these are all approximations. So, because of what I said, because you have a finite time and then you have kind of merging in the dynamical potentials. So I think you could think about the Stackle approximation as another approximation, which isn't terribly much worse than other approximations we're making. And ultimately, I think you have to calibrate this using simulations. Sorry, I'm going to be done just in a second. So this is the kind of thing we have to do, which, I mean, there is indeed an error. That one of the errors we have to look at because of the fact that you have a time-dependent potential, which isn't necessarily integrable.
Okay, I think we'll wrap it up there. It seems like Niayesh has someone wanting his attention. Yeah. So thanks again, Niayesh. It was a very interesting talk. Thanks everyone for participating. And we'll see you all next week at next week's talk on Monday. Same time, same place.
See you, everyone. Take care. Thank you.
Thanks, Niayesh. Thanks, everyone. Bye.
Bye-bye.